Hey everybody, and happy beginning of a 4-day weekend, so that's exciting. Today we're going to look at the start of a new unit, and we're building on the ideas that you already were thinking of last unit as we looked at scale drawings and scale copies, because you were already starting to think about what it means to have things that are the same as each other, even if they're different sizes. And it turns out that although we didn't really talk about ratios and the equivalence of ratios, that is a key component of talking about these kinds of things. So today we're going to explore equivalent ratios a little bit more. First thing I wanted to do was introduce a tool. So this here is a double number line, and as you're looking at this, what do you notice? What do you notice about this diagram? And then what do you wonder about this diagram? One thing that a lot of people noticed was that there are 3 crocodiles for every 4 hippos. There's a relationship between 4 hippos, 3 crocodiles. And that then, relatedly, as the hippos increase by 4, the crocs are increasing by 3. People also saw a cool thing where as you go up, 4 to 3 was -1, 8 to 6 was -2, 12 to 9 was -3, and so the distance between the number of hippos and crocodiles was increasing. People looked at this and they wondered, what could this mean? And some ideas that were put forth that I thought were good were thinking about the population of hippos and crocodiles, maybe in a, I don't know, it would be a super large zoo, but maybe what could be supported on a certain amount of land or in a certain amount of water, something like that. We know that crocs and hippos are in the Nile, so maybe it has to do with space in a river. But that's how a double number line works. It lets you look at a relationship between 2 quantities. I gave you then a double number line that had some things not filled in. And I asked you to complete the double number line with the missing numbers and think about the relationship that you see. People were fairly adept with both the top and the bottom of this number line. They said that this is going up by, oops, that would be an 8 and a 9. That was my bad. 1, 2, 3, 4, 5, 6, 7, 8, ignore that, 9, ignore that. And then along the bottom, you would be going by halves, 0, 0.5, 1.52, 2.53, 3.54, 4.55. So at every point, it turned out that what was on top was double what was on bottom. This is where it's really important to ignore the fact that I just put a 7 and an 8 there. Fail on my part. So then people were thinking about what could this mean. Number 2, I asked you what could each of these number lines represent? What are some quantities that could be related to each other? And because people saw me pouring liquid, some folks started thinking about water and sugar. And thinking about, well, maybe it's a recipe, and every cup of sugar is going to require half a teaspoon of sugar. So if you have 1 cup, it'll need half a teaspoon, 2 cups will take 1 teaspoon, so on and so forth. So then we got into the tasting, and people tasted some different recipes. They ended up having 2 cups to try, and they saw that the darker colored cup also tasted stronger, kind of a little bit sweeter, though neither of them were super sweet. And I gave students 3 recipes and asked them which recipes could be used for each of the things that you tasted. Our first recipe you've got in front of you right now, that's 1½ teaspoons of Kool-Aid mix to 1 cup of water. Our second recipe is half a teaspoon of Kool-Aid mix to 2 cups of water. And our third is a 1/4 teaspoon of Kool-Aid mixed to 1 cup water. When made, they look like this. Looking at this, you might notice that 2 of them have less liquid because they only use 1 cup of water, and 2 of them are a similar color, and we're going to think about what's going on there. Why would the 2 cups and a half teaspoon and the 1 cup with a 1/4 teaspoon end up being the same color? So then I put those recipes in front of students and I said, how can you tell which of these is going to make a stronger tasting drink and which mixture is going to taste different from the others? Students, for the most part, were using still their intuitions about, well, this one tastes stronger, this one looks darker, that idea of there's more of something in it. People were saying that if you have more sugar for an amount of water, that's going to make it stronger. To formalize it, though, it's good to have some diagrams, it's good to have some visual evidence to back you up. So here's one example of visual evidence you could use. You could say that mix A uses 1 cup of water and it uses 1½ teaspoons of the Kool-Aid mix. On the other side, that actually worked for both B and C. those 2 cups of water and a half teaspoon fit with both because it's just one batch of B and 2 batches of C. If you took C and doubled it, now instead of 1 cup, you would have 2 cups of water, and instead of a quarter teaspoon, you would have half a teaspoon. So B and C ended up being the same, and I could have used either of those recipes to make the lighter colored and less strongly flavored drink. Another way to look at it was with a double number line. Making a double number line for A, we saw that 1 cup of water would take 1.5 teaspoons. Looking at B and C, we see that they fit on the same number line. If you do 2 cups of water, that's half a teaspoon of Kool-Aid, and that's B. But if you use 1 cup of water, that's going to be in between 0.5, that'll be a quarter. And so those two things being on a double number line are equivalent to each other. They're going to be the same. A is not. When you get to 1 cup, you are using a lot more Kool-Aid mix than you do for B and C. And then finally, you can think about this as a table. If we're looking at A, if you had 1 cup, that's going to take 1.5 teaspoons of Kool-Aid, where 2 cups, if you doubled that, 2 cups would take 3 teaspoons. On the other hand, B and C, B would be the 2 cups of water with a half teaspoon, and C would be 1 cup of water with a quarter teaspoon. So when you have 1 cup, A uses more drink mix than C because it's 1.5 teaspoons compared to 1/4 teaspoon. And when you have 2 cups of water, A uses more than B because you have 3 teaspoons of Kool-Aid mix compared to only 1/2 teaspoon of Kool-Aid mix for mix B. So I asked students to look at these 2 new mixtures. Kind of gross. I don't know why you would want sweet and salty water. Good thing I didn't give it to anybody. But are these the same? Do they actually end up giving you the same mix? A lot of students looked at mix B and said, well, if I double it, if I just take 2 of mix B, I'm going to end up with the same amount of water as A. I'll have 2 cups of water. The same amount of salt as A, 4 teaspoons of salt. But I will have more sugar than A. Instead of 0.5 cups of sugar, I will have 0.6 cups of sugar. That tells me that they are not going to taste exactly the same. Mixture B is going to taste sweeter because it has more sugar. Then we took it back to scale drawings, and I said, all right, now you've got some ideas about how to compare numbers. Tell me how we could then compare these shapes. What makes A, B, and C different kinds of moons than D? And I got a lot of this kind of language. People were saying that moons A, B, and C are taller and skinnier than D. Their shape is maintained in some way, which is a great place to start. And I said, how could you show that with numbers? And what I'm going to show you next is one example of how you could use numbers to compare. If you wanted to just look at the overall height and width of these, you could draw a rectangle around it and you could say, okay, how wide is it at its widest point and how tall is it at its tallest point? A is going to be 8 by 12, B is 4 by 6, C is 2 by 3, and D is 6 by 4. So then if we take that and put it in, for example, a table, you see that moon C is going to be 2 by 3, and if you looked at the length compared to the width, you end up with 2 to 3 or 2/3. If you look at B, you have 4 to 6. That length to width comparison would be 4 to 6, which reduces to 2 to 3. And A, 8 to 12, reduces to 2 to 3. D, on the other hand, 6 to 4 reduces to 3 to 2, which is not the same as 2/3. So what we're noticing is that you can use ratios to relate your quantities. And if you have relationships that have equivalent ratios, they are going to be the same relationship, just scaled up or scaled down in some way. That meant that C, B, and A are, in fact, the same relationship with a ratio of 2 to 3 when you're looking at length to width. D numerically is not, it's 6 to 4, and you can see that it is longer than the others are when you compare it to its width. So, looking at our first homework problem, if I'm asking you which of these shapes is not like the others, I would want you to make some kind of table, or I guess you could also use a double number line if you wanted, or you could write me a ratio without a table, but I think a table would be useful. And I want you to think about how you can show that one of these is not like the others. and use the idea of equivalent ratios, meaning they are the same in some important way to do that. Have an awesome long weekend. Touch base with me if you have any questions. I'll be available by email.